Hello, you are welcome back. We have our second example on Chinese remainder theorem, and it goes like this one here, which you are required to solve. Well, you can solve this using two methods, and maybe I'll use we have two methods. We have the Chinese remainder theorem or the numerical method. The numerical method. So for me, I will just use the numerical method for this particular question. And so for the numerical method, these two equations, congruences, are of the form x is congruent to bi. Yeah, x is congruent to bi, or let me say b1 mod n1. X is congruent to b2 mod n2, like this. And so we have a table that we use, and so I'm going to draw the table down here and label the headings. So our bi's come here, maybe our xi come here, our ni's come here. Now our b's are our remainders, so we have two remainders, which are 4 and 9. Our x's we don't know yet, but our n's, how do we get our n's? Well, our n's are gotten from, let's say, this one and this one. You multiply them, and so when you are multiplying, you divide by. So let's say n1. If I'm looking for n1, we need to find the bigger one. So let's say the bigger one is n equals to n1 times n2. In this case, we have 5 times 11 is equals to 55. This is our big N. Now let's say I'm looking for n1. Well, n1 will just be the other n's multiplied, but in this case it's just one n. So let's say I'm looking for n1. N1 will just be the value of multiplying the other n. So let's say if I'm looking for the one corresponding to the first one, if there were 3 values, I'll just multiply them. That will be the answer for the first one. If there were the second value, let's say there were 5, maybe 6, and maybe 7 or something. And if I'm looking for this 5, I'll multiply 6 and 7. If I'm looking for 6, I'll multiply 5 and 7. If I'm looking for 7, I'll multiply 6 and 7 in that order. So those are the values. So the first value, since it is just only 11, I'm going to put 11 here, and the second value will be 5 because there are only 2 values. So these are my values of the n's. So now what next? Well, after that we then have to come back and write these n's in this form on our congruencies. So I'll write 11x is congruent to 4 mod 4 or something. Is it 4? Mod 5. Yeah, mod 5. Mod 5. And then 5x is congruent to 9 mod 11. These two. But then with the idea of inverses, I'm looking for numbers such that if I multiply 11 by a number and take modulo 5, I'm going to get 1. So I'm going to start. So this may be the complicated part. So I have 11x1 is congruent to 4 mod 5. But I want a number such that when I multiply it by 11, I'll get 1 mod 5, like this. So what will that number be? Well, that number is just 1, because if I multiply 1 by 11, I'm getting 11 mod 5, I'll get 1. So 1 times 11 x1 mod 11, and this is 1 times 1 mod 5. And so I'm getting x1 equals to 1 mod 5 here. So this is the first one. You remember what I said about here. So because when you multiply a number by its inverse, you get 1. And so that inverse is multiplied on both sides, this side and this side. So we are getting 1 here. That's why you don't see the 11 there again. Is that okay? So we have that one aside. Then we take the other one and write it as 5. Use a different color. Maybe this one. So 5 x2 is congruent to 9 mod 11. So I'm looking for a number such that when I multiply it by 5 mod 11, I'll get 9. Okay. So if you look at all your numbers, well, if I multiply 5 by 5, or 5 by maybe 9, 5 times 9, I'm getting 45. So half 5x1 should be congruent to 1 mod 11. So now the idea of writing 1 here is that I want a number such that when I multiply by 5, when I multiply by 5 and take modulo 11, I'll get a remainder of 1, and that is the inverse of 5. So which number? If I multiply 5 by 9, I'll get 45. Mod 11 divided by 11, I'll get 4 remainder 1. And so 9 5 x1 congruent to 9 times 1 here mod 11. And so since this is the inverse, since it happens that if I multiply this by this, I'll get 1, I just have x1 congruent to 9 mod 11. So now the inverse, so I've got my two x values, so the first x value is this, second x value is this. So I have 1 here and 9 here, like this. So now I'm going to multiply each of these. So I'm going to multiply this, and this on this side. And if I multiply, I'm getting 44 here. Now I'll multiply this, and this. If I multiply, I'm getting 405. Now I then sum them. Now the solution actually is given by x congruent to summation I from 1 up to, since there are 2, that is up to 2 of, here I'll label it as bi, xi, and ni, like this. So, and that will be bi, xi, ni mod mod n, like this. So this is actually the general solution according to this question. So I'm coming to replace them inside this formula. So let me use this color. So I'll have x is congruent to, so summing these two numbers, if I sum them, I'm going to get 449. This is the summation, and that is for this part. So I have summation I from 1 up to n, and in this case our n are just 2, they are just 2 congruencies, bi, ni, xi mod n. We know the value of our n. Our n is 55, of course. We know it's a long time because when we did the multiplication here, we got 55. So right now we have x congruent to, when we did our summation, we got 449. The summation is gotten from the adding this part. 449 mod 55. So we have to reduce this. And how do we reduce this? We take 449 mod 55, and when you do that, you get x is congruent to, the remainder is 9 mod 55. And this is our final answer for that particular question. So we end it here and we continue from the next question. Thank you for watching. Kindly subscribe.